Okay, so now I said we're going to kind of get back into what are we going to have to do for the code here. So let's first kind of write out the block diagram here for reading the pressure. So the first thing here is, of course, we have to provide power to the device, which that's going to be basic because you're literally just going to be connecting it up to your power on the chip. So provide power. This isn't really part of the program. So we, of course, have to connect it up. But then we're going to have to do some kind of start slash initialize is what we're going to want to do. And there might not be much that we do inside there, but there should be some kind of start that we do. And so I'm going to put off to the side here. So for instance, we might call this here, and I like just to use the name of the sensor. So I'm going to have a command MPL115A2 start. And we'll talk more about whether that needs to be void function or not when we actually get into prototyping these out a little bit. Okay, well, once I start slash initialize it, well, this is not really much going on to this. We read pressure slash temperature. And then there's basically, this isn't really a decision tree that we'll have to make. Power, basically, if we still have power, then we go back and we'll continue reading pressure and temperature. And if not, device off. So now there's no commands for this device off here, but what we can see here is, well, we're going to need something to read pressure and temperature. So I'll say read, and instead of writing pressure all the way out, I'll just do press. And then, so we're going to need some function that does that. And then MPL115A2 read temp, and some function that does that. Okay, so that's really all we are going to end up having. As I said, this is a very basic API to start with, and I want to start with a basic one because these can be quite complex, as you'll see when we look at the L squared C1, the I squared C1 for the LCD. It's quite complex, and you have to kind of sort through the data sheet carefully to figure everything out. Okay, so let's kind of think here what we need to do here in these start and initialize things here. So one thing, according to the data sheet, if we go back to the data sheet here, if we look back here at what their block diagrams says, okay, reading the coefficient data. Okay, so that's after the initial power up is to read the coefficient data. And so that could be kind of, here we'll start writing on our MPL115A2. Start. So one thing we should do here is read coefficient data. Because we're going to need that. The next thing here we should say, well, is there anything else that we need to do here? Some people might say, okay, well, the next thing you need to do here is do a data conversion. But, well, remember though, the data conversion is every time you want to take a measurement. So if we did one in the start, it would just be taking one measurement. So I really don't need to take any measurements until, it's asked for one of the functions that are like reading the pressure or reading temperature. Right now, all I'm wanting to do is read the coefficient data. And you might say, well, why don't I put that in the read press or read temp? Well, because I don't want to have to read the coefficient data every single time I do a measurement. I only have to read the coefficient data once. So I should put that in my start. So if that's all I'm going to do here, let's see, is there any information that I need the user to provide me? And the answer is no, because I know what the device address is. It's 60. And so I don't need them to give me an information, so it's a void function. And then do I need to return any information? And this is where you can get into debate. And it's like, technically there's no information you need to return, so we're going to go ahead and do a void function. Some people, depending on what program you're writing, you might have error codes being returned instead. So it's not that you're actually returning a value that's meaningful in the sense that it's data, but it's meaningful in the sense that, well, maybe there was an error while trying to read the coefficient data. But we're not going to worry about that, so we're just going to have a void function. So in my header file, my function prototype is going to be MPL 115A2, void, MPL 115A2 void, and then in the header file, when you're doing function prototypes, you actually put a semicolon after them because that's indicating that's a function prototype for us. So this is going to be in our header file, .h file. We're going to have a lot of other things in there as well. Well, what's the next command here? Well, we have an MPL 115A2 read pressure. And well, this here would be a void function. I don't need to give it anything. The function name itself tells it what it is that I'm wanting to receive. But of course, I should get something back here. I should get, and it's going to be a float. It's a decimal number, so it's going to be a float because I definitely need to get back data. I need to get back what the pressure is. So my function prototype here for this one would be float MPL 115A2, and then there'd be a void inside it, semicolon. And same way, I'm not going to bother writing it down here in black and doing the discussion. It should be really obvious that, well, for the reading the temperature, and I forgot to write the whole thing out here. This is read press void. And then for the read temperature, it's going to basically be the exact same thing, except in this case, of course, I'm reading temperature as opposed to pressure. Now let's talk about what's going to go on inside each one of these functions briefly. For the pressure one, what's going to go inside here is we're going to do a convert command. We're going to read register values, read pressure values. Use formula to compute pressure. And then it's going to be the exact same for the temperature, except instead of reading pressure, we're going to read temperature values. We'll still have to run that convert command because we know we're wanting to take a measurement at that point. Alright, so those are the only functions we're going to write. Now, what we need to do here, and this is where you have to make sure to read through data sheets carefully, is you have to see what kind of numbers that are being given to you. Because these coefficients here, they have a most significant byte and a least significant byte. And it also tells you the size here, that this is 8 bytes and 8 bytes. So that means it's 16 bits. It's 16 bits of data here. And what we need to know is how is that organized, because it's not necessarily just an integer, it's not necessarily a float, and that's what this table does here for us. So let's look at this here. So this table here shows for A0, it's got a total of 16 bits. It's got one sign bit here, so it's got a sign bit. Then it's got 12 integer bits, 3 fractional bits. Okay, so let's look at how we would read A0 in. And this is where it gets a little bit tricky here. So if I wanted to read A0 in, first off, I'm only reading 1 byte of data at a time. So if I think here, let me draw this here. It's not evenly divided, but it's good enough. So this should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16. Yep. And so this would be A015, and this would be A00 as far as what it is. Now this is what we're wanting to store this in here as far as it. Now what it's basically saying is that we have a most significant byte here. So this would be 8. I'm sorry, not 8. This would be 7, 6, 5, 4, 3, 2, 1, 0. And this is the most significant byte. And then this would be 7, 6, 5, 4, 3, 2, 1, 0. And this would be the least significant byte. But the question is, how do we arrange this? How do we get it like this? Well, let's see here. What do we get here? Well, if we read, here, let me say that what we're going to do is we're going to have an int 16 being A0. If we read in here and we just say A0 equals I2C read byte, and there's some information we have to provide in there, and we read the most significant byte first because that's the one that's listed first. The way that's going to look here is we're going to have a bunch of zeros here. 1, 2, 3, 4, 5, 6, 7, 8. And then we're going to have, essentially you would have 15, 14, 13, 12, 11, 10, 9, and then 8 sitting in the lower ones here. That's how it's going to be when we read it in. But clearly that's not where we want the most significant byte to be. We want the most significant byte, we want to shift it over this way. And so what we do here is we actually just do A0 is equal to A0, and then we do the double less than signs, and this is standing for bit shift, and it's like you can think of these as arrows. It's pointing to the right, and so I'm wanting to make A0 equal to A0, but I'm going to bit shift it 8 spots to the right, because if I bit shift 8 spots to the right, I now am going to be having it where I have A15 dot 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 down to A8, but then these are all going to be zeros. So now I've got my most significant byte in the right location, but then I have to say, okay, well now I need to read my least significant byte in. Well, the way you do that here is you would say that A0 is equal to A0, and now I'm going to do a vertical line because this is an OR operation, and I'm going to OR it with another I2C read byte. Because I don't want to say A0 is equal to it, because then it's going to rewrite this whole byte and I'm just going to have the least significant byte in there. But if I OR it with it, well, it's only reading a single byte of data in, and so the upper bytes are just going to be, that's reading in here, are just going to be zeros. But if you OR with 0, you just get what the return result is. So these are all going to stay A15 to A8, but then I'm reading the A7 to A0s in, and so after that, these are no longer going to be zeros. These are going to be your data that you need. So A15 dot 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 all the way down to A0. Now, believe it or not, we're still not done. All we've gotten to this point now is we have gotten in the data from the coefficient, but now I need to convert this coefficient to the right format. And the right format here would be, well, it's got one sign bit, 12 integer bits, 3 fractional bits. So what we're going to do here is we actually say that I'll say A0 coefficient here is going to be this data that we've read in as A0. First off, I'm going to cast it as an integer, A0, and I'm going to divide it by 8.0. And there's a reason I'm dividing it by 8.0. And we'll do this here. I'm sorry. Yeah, that's fine the way it is. I was going to put an extra set of parentheses in, which would be fine to put an extra set of parentheses in here as well, but they're not necessary. So by casting it as an int here, I've converted an integer, but you might say, well, why am I dividing by 8.0? The reason I'm dividing by 8.0 here is that, well, it's got 3 fractional bits. So this is a floating point number. It's got 12 integer bits, 3 fractional bits. Well, how do we get that 8? Well, what is 2 to the third power? 8. And that's where, and actually, I'm sorry, we're not casting this as an int. This is casted as a float, not as an int. I'm sorry about that. The reason you cast it as a float is that this is an integer here, and you want to make sure you're doing floating point division, so that's why you do 8.0. And 2 to the third is equal to 8, which is why we do dividing by 8, because it has 3 decimal points. Now if we go to this, we can see it's going to be a similar pattern for B1, B2, and C12. C12 is a little bit different because it's only got 14 bits, and ADC and TDC are only got 10. Now I'm not going to go into detail on how to do these on paper. We'll do them when we start writing the code. But what we should notice here is that this one has got 13 decimal points, and so for B1 coefficient, we'd have a float of B1 divided by 2 to the, what was it, 13? 13th power. And I actually compute out what 2 to the 13 is. I mean, otherwise you have to have the math library installed and you have to do the Powell stuff, and it's just easier since it's just a constant number. I mean, yeah, it's a big number, but it's not that big. And I just do what 2 to the 13th is, but make sure to put a 0.0 afterwards, otherwise it will do integer division. And then going back here, we can see that B2 would just be divided by 2 to the 4th. Now, what's interesting for C12 is C12 has no integer bits, 13 fractional bits, and 9 decimal point 0 pad. So what that is saying here is, if you're wanting to think about how this data looks for C12, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 0 pads here. So 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, and then we start with the C13. Well, actually, the 13 wouldn't be the one there because that's the sign bit. C12, C11, C10, so on and so on. So how we get with C12 here is you'd have C12 coefficient is equal to a float of C12 divided by 2 to the 9 plus 14, I believe. I have to go back here. No, 9 plus 13. 13 fractional bits, 9 sign bits. So 2 to the 13 plus 9 which of course is just 22. So that's what you would want to divide by. Now, oftentimes in programs, you don't have to necessarily do these conversions. In other sensors, it will just say, hey, I'm returning a 16-bit integer. And so all you have to do is read that in, and there's nothing you have to do. Or sometimes they'll say, okay, it returns a floating point, number, and so you just have to read it in and cast it as a floating point number. But in this particular case, with the coefficients, the data sheet told me, hey, there's some special things I have to consider about. And it even goes through here and gives you an example of how these are done as far as integer bits and then fractional bits, and you can even see here's where all those zero pads were that we saw. And you can see the fractional 12-bit and everything, and that's where we got the 2 to the 3rd here, 2 to the 13th, 2 to the 14th, and then this was 2 to the 22nd, is where we got that from. And we will talk about the pressure and the temperature one just in the program. Alright, so that's enough here. What we're going to start in the next set of videos here is actually starting to write some code with how to actually start writing code for this temperature and pressure sensor.